So, thank you everyone coming to my talk. And the outline of my talk is I will briefly introduce some background and motivation of my study, and then I will give a brief introduction on the LiDAR I'm working on, and also I will have like 2 case study working with using the LiDAR, especially for the LiDAR in the Amazon forest. And okay, let's get started. So first, we all know the Amazon forest is big. It's kind of 1.4 million acres, about 3.7% of the land surface, and it have very large carbon stocks in the land ecosystem. And also the Amazon forest is green. It produces about 20% of the world oxygen, so it's really important ecosystem, and it has a lot of it play a really important role in the energy surface energy flux, the hydrology circles, and also the carbon circles. So the Amazon forest actually is changing a lot during the past several years or decades. Based on this map from the Global Forest Watch, we can see that there are about 9.8% of the forest in Brazil is lost. And based on the map, the green part is the forest cover and the pink part is the loss. It's the loss of the forest cover between 2001 and 2017. And we can see that most of the lost part is within or close to the Amazon basin. And there's a couple of reasons for this loss. It can be the extreme weathers, it can be the effect of climate, and it can also be the land use change. They're converting the forest to some other land cover, like the agriculture, and also it can be some effect on the policies. When the policymakers change their policy, they may affect they may increase the forest loss of the Amazon forest. So yeah, there's so many reasons, and it's really unknown which one is the major driver for the forest loss. So my kind of interest, my research interest will be focused on if we can quantify those changes in more details, so we can know what is the major driver of those changes. So for the forest structure, how can we quantify the forest structure? Like conventionally, we just send people in the field and send them into the forest to measure those trees. And then with the large demand of the larger spatial coverage of the forest inventory information or structure information, we have introduced the remote sensing techniques to assist the forest structure estimation. And yeah, LiDAR is one of the most primary resources for the remote sensing techniques for forest assessment, and I will use several slides to explain why it is important and can be used as a primary resource for the forest assessment. So don't worry about this figure right now, so I will have more details later. So what is LiDAR? LiDAR stands for the light detection and ranging. You can also write it in different ways, or we call it LiDAR, like laser detection ranging. Also, someone call it laser scanning. It's usually just have a laser sensor and shoot a laser beam on the ground, and it will be intersect with some objects above ground, like the tree there, and also may have the possibility to touch the ground. And the red beam there is kind of what we call the footprint, and this energy returns is kind of full waveform of the LiDAR, and the red point is the discrete point of the LiDAR if we save the data into the point cloud. And there's a lot of types of LiDAR. So from the space, we have space 1 LiDAR, and if we go a little lower, we have the space shuttles and the airborne LiDAR. And if we go to the ground, we will have the scanning. We will have scanning lasers, and also the PCL, the profiling canopy lasers, LiDAR. And each of the LiDAR have their different characteristics and their specialties. For the spatial LiDAR, they will give a really large footprint, so each beams will be covered like more than one trace. So you will get an estimate of the forest structure at kind of relatively to the plot level, and it can cover a very large spatial area. And for the ground-based LiDAR, the terrestrial LiDAR is kind of a scanning laser, so they will receive like thousands or over laser beams per second, so they will have a really high detail of the forest structure, especially for the woody part. That is very good for the forest inventory information. And also the PCL, the profiling canopy laser, LiDAR is kind of using a handheld rangefinder to let the laser facing about up to the canopy and get some information of the structure, get the canopy informations. And then in the middle is kind of the airborne LiDAR. It's just use the airborne to carry a laser sensor and then fly about 3,000 meters or between or under 500 meters. So they will give a very high details of the forest structure and also have a really decent of the canopy coverage. And in the following slide, I will be majorly focused on the airborne LiDAR and to see what's the advantage of the airborne LiDAR for the forest structure analysis. The first one is accuracy. The LiDAR can provide a very accurate terrain or ground surface information. Like they can get a really high resolution of the ground, so you will have a better estimation of the forest structure. And also you can do some other things like have a better stream flow simulation for other purposes, and also for the erosion detections. The other thing is the vertical structure. That's the most important part of the LiDAR. So it gives the opportunity to access the vertical structure of the forest without touching it. So with the vertical structure, it makes it possible for a lot of things, for the forest inventory or the forest measurement. It can get some chrome information, or even if the data collecting from the leaf-off season, you can still do the chrome reconstruction to get the chrome information. And also it can detect the canopy gaps, and also the gaps with young regenerations, which is really challenging using the spectral information, the spectral image to do that. And also you can get the stems and the DBH information after you have the crown, and you can get the crown relationship between the DBH and also the stem position of the trees. That will be suited for the remote forest inventory. And also you can get the biomass. And this is the biomass map in a temperate forest in Indiana, and the other part is the soil information with different productivity. So like combine the soil productivity and the size and the metrics from the LiDAR, you can get a very good biomass estimation. So this slide is almost summarizes my work, my PhD work at Purdue. And then moving forward here, we have like better details of the forest with better quality data. So that makes it possible to try to analyze the tropical forest with different structures, different stratas, and also make it possible to analyze some leaf conditions, like leaf profiles, that's the leaf area vertical profiles on the left. Yes, left to me here. And also another advantage of the LiDAR is the spatial and temporal coverage. It was an advantage until the recent years, maybe recent 5 years. because more and more data is available and more high quality data is available. So that makes it an advantage for the data analysts right now, and take the data I use for the following study, the Sustainable Landscape Review project. It's a really good data set with a large survey coverage. It's about 9 years survey from 2008 to 2017, covered like more than 65 sites, forest sites, or sub-sites. And also it has over 100 LiDAR surveys, and the average LiDAR quality is very high, and they have a high density LiDAR data, and they also have a lot of forest inventory data. And also there's a lot of repeat surveys. Like someone they have a 2 times revisit, and some they have 4 times revisit for the data set. So it's a very good multi-site and multi-temporal data set. Then with the profile, with the leaf profile techniques, and with the good data set with the multi-temporal coverage, we can actually do the repeat estimation of the leaf area vertical profiles. Actually, it's also called LAD profiles. So yeah, this is survey 1 and survey 2, and we can get two profiles from the 2 survey, and the red ones stand for the first survey in 2008, and the blue profile stand for the second survey from 2012. And compared the 2 profiles, we found there's some difference. Like the second survey have a kind of a lower profile compared to the first survey. And when we check on the forest structure, especially for this part, we see there's some like a tree loss there. And yeah, the next question is, can we claim this is structure change, and the structure change makes the profile change like this? Maybe not. Because if you see more details about the 2 data sets, the sensor of the LiDAR is kind of different, and also they have a different quality. Like this point density is twice, like 15 points per square meter. That one is 25 points per square meter. It's about twice much at the second survey. So there may be something there that may be effect to the LAD profiles estimation. So that brings to my first case study. Okay, just another slide. Like, yeah, it's very challenging when you're using multi-site and multi-temporal data set, because the data set may have different sensor. Yeah, also the scanning pattern may be different, and also they may have different population densities. Some is very dense, some is not. It's kind of low density. And also they may have a different coordinate system. You can't even just directly match them up when you do the comparison. So yeah, that's bring the first case study, like how we can using the multi-temporal and multi-site airborne LiDAR to estimate the leaf area profile, and also will the sensor have any effects, like what I mentioned in the previous slide, have any effects on the chain of profile and the estimations. So yeah, this is the 4 sensors used in the dataset. I'm using the Sustainable Landscape dataset in the Brazil project. They have different flying altitude. Like one is very low, and the other 3 is very similar. And they have a different beam divergence. This beam divergence, you can see it's like a beam energy. If you have a small number, you have a strong energy. If you have a large number, you have a low energy. And also different scan angle. They have like 10 degrees scan angle, and that one is 13. It's all different. And also they have different footprint. Some footprint is large, some footprint is small. That means the touch area of the canopy may be different based on the footprint. And also the pulse density is still varied. Some is very consistent, like all average, like 15 points per square meter. And some is very varied, like they can vary from 20 points to the 16 point square meters. So there's a lot of difference between those sensors. So what we want to do is, if all those variables have any effects on the e-variable profile estimation. So in sum, there may be like some reason why the profile is different. The first one is the real biophysical changes. Like the tree there, we are losing trees, so we have the difference. Also the survey parameter, like the point density, the different positivity may have the effect on the e-variable profile, and also different laser systems. Then we can have a model there that include all the three factors. That's the profile 2 will be different from the profile 1 because of the change, the survey parameter and the sensors. And then what we want is to focus on if the LiDAR sensor will have any effect there, because this one is already like there's numerous study that working on the pulse density and effects, and they will be see pulse density is not very much sensitive after they have like 4 point square meter or 10 point square meter. The figure is very small, but yeah, you can see this is 10. So after we see after the past 10 point square meter, it's almost just have no effects. And based on our data set, most of our data set is higher than this threshold. So we're not expecting too much difference in that part. But to keep forward, I will be also take consideration in the following slide. So now I want to reduce the first part is about physical change from the model. So I just try to focus on the forest with no structure change, just do some spatial sampling to figure out which part they don't have like significant canopy change. So then I just assume there will be like undisturbed forest, there will be no significant structure change. So the C in the model will be close to 0. So the model can only have effects of the pulse density of the sensors. And to reduce the effect of the pulse density, I just do some thresholding algorithm to increase the pulse density during the sample program, and then when it goes to certain thresholds, I will just assume the pulse density will have no effect or will have minimum effects on our model, and then the profile within our sampled area will be only focused on the sensor area. And then, yeah, after sampling, we do some linear regression between different sensors and between different sites of the profile. So we figure out do you have some consistent difference between the profiles that's estimated from different sensors, and the blue arrow is the direct comparison using just comparing the profiles from one sensor to the other sensor, and they will have a kind of difference there. Like this one is 6.95% difference of the profile, and this one is a little bigger. The LTM 2003 and the LS50 is a little bigger. It's like 18% of difference, and the gray arrow is kind of from one sensor to the other, and then to the other one. It's kind of indirect comparison. Like we transfer the arrow from one sensor to the other one, and this one will be the blue arrow will be the direct comparison between the two sensors. So we can see it's pretty close after we do some validation there. So that means the sensor can introduce the bias, and the bias is kind of pretty consistent, and that means it is a practical bias. So back to that curve, back to the profile we saw earlier. After the sensor correction, we see those two profiles they pretty match up well. So that means the difference here may not the biophysical change due to the one emergent tree lost as we see earlier in the slides, it may be just some sensor effects. And we do multiple sites to validate if our calculation is right or not, and we choose like 16 pairs from different sites. It's about 9 for the site and 16 pairs of repeat measurements. And we found pretty consistent result here. So yeah, that's proof that the sensor do have some effects still here, but it's practical. And also after the correction, we have a very reliable and consistent AI estimation, the leaf area index estimation. You see the correlation between the first survey and second survey is pretty similar. And before that, there will be just barely no relationship between the LAI, between the first survey and second survey. And same for the mean LAI. No relationship before correction and strong relationship after correction. What's interesting is when we compare the LAD profiles, they show some difference between the as we increase the survey interval years. Like if we have 9 years interval of the repeat measurement, like one survey is surveying the 2008, the other one is in 2017, we have a very low correlation, and the difference, the standard deviation, the difference will be very high. So that means the leaf area profile is changing through the time. But based on what we know in the previous slides, the LAI is not changed. So it's pretty interesting finding there, and that's also lead to the second study of my work. And this is a brief summary about the first study. It's a sensor to introduce bias on LED profile, but it's kind of correctable using some simple linear regression. And also the after correction, the mean and max LAI is consistent in the repeat method, but the difference between the LED increase over time. So yeah, that's make me thinking about, based on the maps, that made me think about, yeah, we have some like forest change there. We have tree loss, and we may have the profile change because of tree loss, but the LAI is consistent. That maybe stand for there may be some regrowth and to compensate the loss of LAI. But the profile actually really changed from like top to bottom. So how to validate this kind of information? I want to see if I can get some individual chrome from the data set. If I can isolate every tree from the LiDAR, then I will do the comparison to see how much trees we lost and how much trees we have with growth after several years. And then I will know if this is true difference, true disagreement, or there will be some, or it's just someone is wrong. So yeah, that's why I want to do the case study 2, the meta-analysis of the overstory prone delineation in the tropical forest. So the first step is try to figure out different methodology, like some potential clusters or some potential algorithm to do that, to test how they work in the tropical forest. And I'll just show one result using the mean shift algorithm. And it's pretty similar like the Antonio Fraz 2016 paper. They use the different mean shift algorithm for the overstory and for the large trees and small trees. And I do something similar like this. And first, just get some cluster running in the data sets, and then to see, and then define which cluster is belong to a tree, which cluster is belong to a sub, which cluster is sub of the tree that need to merge to the neighborhood, or which one we should remove. Just some algorithm like this, And then with the individual tree crown information, we will have the canopy height information here and the crown diameter information here. And using the DBH equation from the chapter 2017, so we can have the DBH distribution after the individual tree crown delineation. So yeah, here is some like preliminary results of the individual tree crown delineation. Like the top part is the original LiDAR point cloud, and the bottom is the individual tree crowns. Different color indicate different trees there. You can see some big trees is quite obvious, they are separate, isolated, but yeah, still some challenging there in the mixed and kind of lower canopy in the dense part. So yeah, still a lot of things to work on. This is just some preliminary results, and this study is I'm still working on this one. And yeah, we compare the canopy height information between the inventory data and the LiDAR-based estimation. The top part is the LiDAR-based canopy height distribution, and the bottom is the distribution from the inventory data. I mean, this one is incorrect inventory because in the inventory data they didn't measure every tree in their plot. Like they just measure small trees with a shorter distance and then measure larger trees with a larger distance. So that makes things it's not a full information about canopy height distribution, but it's partial. So I still try to figure out a way how to try to make them reflect to the real distribution of the forest. But yeah, it's still working on that. Similar to the crowns. Yeah, they have some similar distributions, but you see it's it's much higher here compared to the DBH class here. Similar reason maybe, and yeah, need better data to think about it, or need a better way to fix this distribution, and then I will know how accurate my estimation is. And this one is kind of a relationship between the DBH and canopy height. The red point is the LiDAR-based estimates, and the blue point is from the inventory. So yeah, we can't just directly compare the histogram because the uneven distribution of the sampling. So sampling issue. So I just try to compare the relationship between DBH and canopy height. So yeah, it looks pretty similar actually, and they have some similar relationship between DBH from the LiDAR-based estimate and the inventory data. And yeah, and then as I said, it's a meta-analysis. I will be test some other algorithms to figure out if there are some better algorithms. Like the first three is kind of the first two is kind of a 2D algorithm, and the third and the fourth will be like 3D using the 3D on cloud information to do the estimation. So yeah, after I compare several results, I will know which one will be the best algorithm to do that. Yeah. Then what's the next step for this study? Like, yeah, I will try to do the crown, try to delineate the crowns at a different forest site. And also I will try to do the multi-temporal crowns using the data to see if I can pick up the tree at the same location, and if I can pick up the tree loss, or if they have a tree growth. When I compare the results from the repeat surveys, and also try to link the individual tree information, the crown information with the LED profiles to see how much the tree crowns I delineate to contribute to the LED profiles. And also, yeah, after we have the individual trees, I will work on some like individual prompt-based biomass estimation to see if it would be better to think about the individual tree level structure information for the biomass estimation. Yeah, so yeah, like I said, this is the two case study I present in previous slides, and after I finish the individual trees, I will be trying to work on the set structure, which means will be to see how the forest is different from the different location and then for the biomass. This is kind of the concept of the set structure, like try to test different sites and to see if they have different composition of the tree demographics, and then I'll see if my algorithm, like the individual algorithm, can improve the biomass estimation when using the LiDAR data. So yeah, that's all I want to talk today. So I want to thank Dr. Lab, thank everyone helping me a lot. And also thanks for the funding and the support in Brazil. Yeah, let's see any questions.